The form of complex numbers, when we write them as a real part plus an imaginary part, a plus bi, that is called a Cartesian form. And it's called a Cartesian form because we can place points in the Cartesian plane by associating the vertical axis to the imaginary axis and the horizontal axis to the real axis. There is another way to represent these points. It's called a polar form. Polar form says a point somewhere could be identified according to its A, B coordinates, according to its real part and imaginary part, but you can also identify it according to the length of the vector, the modulus, and the angle that it makes with respect to the real axis. And when you use this notation, you would write z as r times e to the I theta. E being Euler's constant, it's the exponential. R is a real number, theta is the angle here. We also write it like this. And I think I've seen some English books also write it CIS of theta. Cosine I sine theta. That's not a notation that I'm going to use, but you might have learned that in high school. At any rate, this here contains the same amount of information as the form a plus bi or x plus iy, which is a different way to present it. In fact, what's the link? Well, if you take any point, let's go back to this point here, and we're gonna call these coordinates, these lengths x and y. Well, we remember from trigonometry how to link x and y with the angle theta. Like we know how to compute, say, the cosine of theta. So this is the right angle triangle. Cosine of theta is the adjacent side. So the adjacent side to the angle is x divided by the hypotenuse, which is r. And the sine of theta, you look at the opposite side, which is y, divided by the hypotenuse, which is r, the length of the triangle there. So we have formulas that link x, r, theta, and y. And by construction, r has to be the length of z. I mean, they're representing the same quantity. If z is your point, your complex number here, whether I call this r or the modulus of z, this is the length of the vector here. And by Pythagoras' theorem, that's got to be the square root of x squared plus y squared. So if I write z as x plus yi in Cartesian form, and I know that x is equal to r times cosine theta, and y is equal to r times sine theta, then this becomes r times cosine theta for the real part, plus I times r sine theta for the imaginary part, which then I can write by taking away the r, which is common to both the real part and the imaginary part, as r times cosine theta plus I sine theta. That's the polar form. When you write complex numbers this way, we have two parameters, r and theta. Theta, the Greek letter, we call the argument of the complex number, and r we call the modulus, or the radius, or the length. One thing to keep in mind, though, is that the argument is not unique, right? If you go back to the original statement here, whether I do an angle of theta to get to this point, or an angle of 2 pi, so 2 pi radians, plus an extra theta, I'm going to get back to the same point here. 2 pi representing a full rotation. these two will give me exactly the same z. That's a bit of an annoyance. We like to have unique representations. Well, in order to get unique representations, we typically pick the argument to be between minus pi, so minus pi is 180 degrees, and pi, with these inequalities here. And we would write this theta as the argument of z, but we'll use the uppercase A to recognize that we're talking about the specific argument, the principal argument, the one that lies between minus pi and pi. I don't know if you remember what these things represent, but just take a few seconds here. This is 0 radians. If you go all the way up to here, you've gone pi over 2 radians. If you go all the way up to here, you've gone pi radians. If you've gone all the way up to here, it's 3 pi over 2. And finally, back to 2 pi radians. And you could also do it the other way. I mean, who's to stop you? This is 0. This would be minus pi over 2. This would be minus pi. This would be minus 3 pi over 2. And this would be minus 2 pi. So when we say that the angle is between minus pi and pi, what we mean is you start here, like if you're here, you would actually go from this point to this angle. This is what your theta would be. You would not go the other way, because if you go the other way, you're going to up minus pi, and it's going to be a little bit more than minus pi. So you pick the shortest path, starting from the positive real axis. Not something we're going to see in this class, but something you'll see in your second calculus course and in complex analysis and differential equations when you see these things. But we have a way to write the exponential. The exponential of z would be 1 plus z to the 1 divided by 1 factorial plus z to the 2 divided by 2 factorial, and so on. We write this in series form as the infinite series of z over n divided by n factorial when n goes from 0 to infinity. That's the exponential of z. If you were to also do a power series expansion for cosine of theta and for sine of theta, you would find that e to the I theta is exactly the same as cosine theta plus I sine theta. Here, I have to ask you to take this on faith if you haven't yet done it, but it's a way for us to simplify the writing of the polar form, which was r cosine theta plus I sine theta. This expression here from calculus, we will eventually see is the same thing as e to the I theta. And so the polar form would be r times e to the I theta. There'll be a diagram on the next slide. I'd like you to check that 2i is actually the same thing as 2e to the I pi over 2. That minus I is the same as e minus I pi over 2. That minus 1 is the same as e to the I pi. And that 1 plus I is the same as square root of 2 times e to the I pi over 4. In these four numbers, the term on the left is a Cartesian form of a complex number, and the term on the right is the polar form. So at first glance, these numbers look like they're completely different, but they're not. They're actually representing the same numbers. I mean, that's four different complex numbers here, but both the left-hand side and the right-hand side represent the same number. Some of the properties of the complex numbers are very easy to state if you use polar form, right? If you write that two numbers are equal in polar form, then you have to have that their modulus are the same, or moduli, I guess I should say, and that their angles are the same up to a multiple of 2 pi. The complex conjugate, very easy. I've told you what happens when you deal with z and you have the complex conjugate. You go in the expression for z and you transform every I into a minus I. So we had r e to the I theta, and I just take the I that is there and I'm replacing it by minus I. There's my complex conjugate. One nice property of complex forms as well is that the absolute value, the modulus of e to the I theta, is equal to 1. Cos theta plus I sine theta in absolute value is equal to 1. Why do I know that? Well, if I write it in Cartesian form, e I theta is cos theta plus I sine theta, and then there's my real part, cos theta, there's my imaginary part, sine theta, and the modulus of a plus ib is the square root of a squared plus b squared. Without the I isn't there in the modulus. And then, well, what's a squared? That's the square root of cosine. And what's b squared is the square root of sine. Sorry, what's the square root of, what's the square root of a squared is the square root of cosine, b squared is the square root of sine. That's what I meant to say here. So I have cosine squared theta plus sine squared theta. The I doesn't appear. That's the same thing as 1. You remember from calculus. It's good news. Where complex numbers in polar form really shine is when the time comes to multiply them. See, Cartesian forms, very good for adding complex numbers together. It's vectors that get added together. It's very easy to add vectors together. Not so great for multiplication. Polar form, great for multiplication. For addition, not so great either. How do we actually work with them? Well, we have to remember one of our trigonometric properties that tells us what the cosine of a sum of angles would be and the sine of sum of angles would be. If you write both these two numbers, z and w, in polar form, so r times cosine theta plus I sine theta, that's z. And s times cosine phi plus I sine phi, that's w. You do the product, right? R and s, these are scalars, real numbers. You can place them together. Then we have cosine theta times cosine phi, we're doing FOIL, plus cosine theta times I sine phi, plus I sine phi times I sine theta, times cosine phi, plus I sine theta times I sine phi. You put all of those together. Cos theta, cos phi shows up here. Sine theta, sine phi times I squared. That's minus sine theta, sine phi. So right here. Then I have I times sine theta, cos phi right here. And then cos theta times I sine phi right here. Now, you may not remember those as the cosine and the sine of a sum of angles, but that's what they are. Right? This thing is just the cosine of theta plus phi, and this other thing here is the sine of theta plus phi. And now I'm back to an expression that looks an awful lot like a polar form, right? I have some real number, in this case rs, times the cosine of something plus I sine of the same something. And that's just writing r times s, the real number, the modulus, times e to the I theta plus phi. When you multiply numbers in complex form, all you have to do is to multiply their moduli together and to add their arguments. Division is also multiplication of exponentials, right? Z divided by W would be R divided by S. These are the moduli part. And then e to the I theta divided by e to the I phi. And that's literally I theta minus I phi. That's how we divide exponentials. So, can we simplify or compute what I over 1 plus I would be? I mean, I over 1 plus I is an honest-to-goodness complex number. It's just, it's not in the form that we recognize. Right? We wrote complex numbers as numbers in Cartesian form or polar form. This isn't it. So can I write them either in polar form or Cartesian form? We've just mentioned that the polar form is indicated when you're trying to multiply or divide numbers. Why don't we use the polar form here? So we'll write I in polar form. The modulus of I this bit here would be what exactly? It would be the square root of the real part, but I has no real part, so that's 0 squared, plus the imaginary part. That's the same thing as writing 1 times I. So R is equal to 0 squared plus 1 squared, which is 1. So the modulus is 1. What about the theta? Well, we need to find the angle that corresponds to I. I can go here and say, well, this is where I would be, the point I. And what's my angle? I start from here and I go all the way to I, and that's an angle of pi over 2. So my theta would be pi over 2. So this number I is in fact e to the I pi over 2. What can we say about 1 plus I? Well, it helps as well to be able to place it somewhere. So 1 plus I is this point here. 1, 1. This is 1 plus I. It has the same x and the same y coordinate, or the same real and the same imaginary coordinate. So this angle here has to be 45 degrees. 45 degrees in radians is pi over 4. So the angle is going to be pi over 4, and the radius will be the length of this thing here. We use the theorem. This is 1, this is 1, so this has got to be the square root of 1 squared plus 1 squared. That's the square root of 2. So I is equal to e to the I pi over 2. 1 plus I is equal to square root of 2, e to the I pi over 4. That's how we write numbers in polar form. And when we do the quotient, well, if I put them in polar form, I have e to the I pi over 2 divided by square root of 2, e to the I pi over 4. I take the moduli. This is really 1 divided by square root of 2, right here. And then I do I subtract the angle in the denominator from the angle in the numerator. That gives me e to the I pi over 2 minus pi over 4, which, when you simplify things, and we're expecting you to be able to simplify this without a calculator, pi over 2 minus pi over 4, I don't care what its numerical value is, you need to recognize that this is 90 degrees minus 45 degrees. That's 45 degrees pi over 4. If you were to divide I by 1 plus I using the Cartesian formula, which you can, and we just did it a few slides back, you would get 1 plus I over 2. Now, it shouldn't matter which approach you pick, the answer should be the same, and that means that 1 plus I over 2 is the same thing as 1 over square root of 2 times e to the I pi over 4. There is a result in algebra called the fundamental theorem. It tells us something about the number of roots you may expect from a polynomial of degree n. That's not a linear algebra result, that's just a general algebra result. Every quadratic polynomial has 2 roots, right? It's assuming that whenever you have 1 root, you count it as 2 distinct roots. Either you get 2 distinct real roots, 1 double real root, and 2 distinct complex conjugate roots. But if you want to find a polynomial with a given root z, you can easily build one. As simple as multiplying x minus z by x minus z bar. In fact, if you do that, you'll get a polynomial of degree 2, right? The exponent with the x is 2, and the roots are going to be z and its conjugate z bar. Now this polynomial here is a polynomial with real coefficients, even though it is expressed with the help of complex numbers, right? We know what z times z bar is. That is just z squared, or the modulus of z squared, or the square of the modulus of z. And we know that's a real number. That's the square root of a squared plus b squared, which is real. The bit that's perhaps less obvious is that z plus z bar is also real. Well, if z is equal to a plus bi, and z bar is equal to a minus bi, which is how a number and its conjugate are linked, then z plus z bar would be a plus bi plus a minus bi. Bi minus bi cancels out. You end up with 2a. A is the real part. Twice a real number is itself real. So we have here a real coefficient, a real polynomial of degree 2 that has a specific root z and its complex conjugate. Every real polynomial has complex roots, remembering that real numbers are complex numbers. And every complex number is the root of some polynomial. If z and w are complex numbers, but they're not conjugates of one another, the polynomial x minus z, x minus w will be a quadratic polynomial. It is going to have, however, complex coefficients. In order for the coefficients here, this bit and this bit to be real, there's got to be a special link between z and, well, the other thing here. Z that links it is z bar. But if I just pick z and w, that product is going to give me a complex coefficient. Now, if you remember at the start, we added an I to the list of numbers because we wanted to be able to find the root of x squared plus 1. That's not really how complex numbers were built, but roughly speaking, this is what's happened. X squared plus 1 didn't have a root. We wanted one. We called it I. If you were to take all of the quadratic polynomials with complex coefficients, the things that we've added these i's to stuff. So now we have these new numbers, complex numbers, and we consider coefficients that look like this. Ax squared plus bx plus c, where a, b, c are complex numbers here instead of real numbers. Would we need to add anything like an I in order to be able to solve this? And the answer is no. I, which is the very, very simple and simple root of x squared plus 1, is enough to give you the solution of every polynomial with complex coefficients. We do not need more in order to be able to achieve solutions. That's the fundamental theorem. Every polynomial that has coefficients in C will factor completely into linear factors, terms that look like ax plus b, where a and b would potentially be complex numbers. Those of you who study mathematics, you will see, however, that even though the complex numbers here are complete according to the fundamental theorem, there are number systems above the complex numbers. Just as the complex numbers was a superset of the real numbers, we have something called the quaternions, which are a superset of the complex numbers, and the octonions, which are a superset of the quaternions. When you go from the real numbers to the complex numbers, you gain the ability to solve all quadratic polynomial equations. But you lose something, right? You lose the ability to say when a number is greater than another number. When you go from the complex numbers to the quaternions, you gain, well, you have more numbers, which is good, but you lose the ability, or you lose the property that the product is commutative. Like with real numbers and complex numbers, when you multiply a times b or b times a, you get the same outcome. In quaternions, that's not the case. And in octonions, you add more numbers, but what you lose is associativity. So whenever you study group theory, which is also something that people in physics will study, you're going to get introduced to quaternions and non-commutative groups, as opposed to abelian groups.